Hello and welcome to Section 8, Bayesian Parameter Estimation. There are some drawbacks with using the MLE method. We saw that the MLE approach assigns an absolute zero value to parameters whose corresponding instance does not show up in the data set. If you recall the formula, if we don't see any instance with the value of x and parents of x appearing, well, this nominator here will be equal to 0, and that means that the corresponding event corresponding to the parameter theta x never happens in reality. This is a very strong statement, which is often wrong and just a consequence of a limited data set that we used. This is also particularly problematic when there is no instance in the data set on the parents making the denominator equal to 0. Then I cannot even use this to get a 0 value. Now, on the other hand, if we have some prior knowledge about the parameters, MLE does not allow me to incorporate them into my parameter estimation. For example, imagine I have an unfair coin and I know it's unfair. Now, if I just toss the coin 2 times and it appears that one of the tosses is head and the other is tail, then MLE will tell me that the coin is fair. My theta value, the probability of head, will be 0.5. And this is despite the fact that I somehow, from prior knowledge, maybe someone has told me that this coin is unfair. So the question is, can we incorporate our prior knowledge about the parameters in the estimation? By doing this, we may be able to solve this issue I raise here. Because if I'm sure that an event will happen in reality with some non-zero probability, it's impossible that it will never happen, then this is some kind of prior knowledge that I can hopefully incorporate into my parameter estimation and avoid this case of an absolute 0. So is there a way to incorporate this? And the answer is yes, via the posterior distribution. Recall, prior and posterior distribution. If we treat theta as a random variable, then by using the Bayes rule, I can have this equation. P of theta condition on D is P of D condition on theta times P of theta divided by P of D. Now, this term here is our likelihood that we defined in the previous sections. This term is the posterior probability of theta condition on D. It's the opposite of this one. And this is the prior parameter distribution. The probability of the parameters theta not condition on anything and not anything condition on it. And P of D is the probability of data, which acts as a normalizing factor and can be calculated by marginalizing theta from the nominator. We have seen the formula for the discrete case. This is just the continuous version. So we'll have the nominator. This is just P of D and theta. And I'm integrating it over theta. The posterior is a distribution, not a single value. Okay. So similar to MLE, one may use the mode, for example, called maximum a posteriori as the optimal parameter. So one may define theta MAP as argmax of this posterior distribution. And we can use this. This is sometimes used in practice. The mean or any other statistics may be used as well. So we can take the mean of the posterior and use that as the optimal value. Now, the main difference between the posterior and the likelihood is that the posterior additionally includes the prior. Okay, of course, we have this normalizing factor, but this is a key term here. If the prior is a uniform distribution, meaning that P of theta is equal to 1 for all theta, then the posterior is just the normalized likelihood function. Okay? So the question is, what is the difference compared to the MLE approach when we use a uniform prior? Is there any difference? Let's see. Assume that we have n coin tosses, x1 to xn. Let theta be the probability of heads. This should be familiar to you. We want to use the mean of the posterior as the optimal value for the parameter theta. So how can we calculate the posterior mean? It's theta, but not times P of theta. That would just give us the average value of theta, the mean or the expected. This is the posterior mean. So we multiply it by the distribution of the posterior, not the distribution of theta. So I will have this. This will be my decided optimal value, and I want to calculate it. Okay, so for a uniform prior distribution, I can use the formula I had for the posterior, and P of theta, the green part, will be 1, so I will just replace it with this term, the likelihood divided by P of D. And P of D is independent of this integration. I will take it out, and I will have this term. The likelihood we already calculated. So if we have n of h times head, I will have theta to the power of nh, and this is the number of times that tails happen, so I will have 1 minus theta to the power of it. So I have this formula, and I will rewrite it here. I will use it later, so this I noted with a star. Using integration by part, I want to calculate this, and I want to somehow make theta bar appear on the right-hand side as well to make my calculations easier. So that's why I want to use integration by part. So if I call this u v prime, the derivative of v, then I can write it as the integration of u prime v minus uv. This was also the integration. Now, to double check this, just note that if this is my u, if this is v, then u appears here and v prime appears here as well. This is the derivative of this term. Nt plus 1 will appear as a coefficient and will cancel out with this denominator, and I will have 1 minus theta to the power of nt. U prime v similarly can be calculated, so this will appear as a coefficient, and n of h, and v will appear exactly as it is here. The point, however, is that this part is 0, because if I replace 1, this will be 0. If I replace 0, this will be 0. So I'm just left with the first part, this integration. I am rewriting it here, and you see that these coefficients in the denominator and numerator, they can be taken out, which I did here. So I will be left with this integration, and here I will take one of the powers here out, 1 minus theta, and then break the integral into two parts. Okay, so I will have 1 times this minus theta times this. So here theta appeared with an additional power. This is my likelihood function. I knew it. I used it in the first stage. What about this one? Well, this is where I want to use that star that I just mentioned. So I had it right here. The star, this equation, I got that theta bar is equal to this, and I managed to get it appear again here. Okay, so this will be simply theta bar, since I'm factorizing over 1 over PD, so I have to put PD times theta bar here. Great. Now I can rewrite this in this form, because PD cancels out, and now I have theta bar here being equal to some number minus some coefficients times theta bar. If I simplify it, I will get my value for theta bar. nh plus 1 divided by nh plus nt plus 2. So the mean of the posterior, which is my optimal value, I decided to use this as my optimal value, is this. Now, if you recall, the MLE was this. What's the difference? Well, there's 1 here and 1, 2 here, so they didn't show up in the MLE. So what's going on? It is like the expected posterior is the same as the MLE prediction, except that it adds 1 imaginary instance to each count. So NH is added by 1, NT is added by 1, and here I will have NH plus 1, here I will have, each of them have 1, so I have plus 2. So it's like I'm adding those plus 1s, 1 additional instance to each case. Recall in the first section we faced the situation where we didn't have any instance for one of our values, and then we said, well, in this case the probability is 50%, or it's equivalent to adding those instances. This is an explanation, an intuitive explanation for why that is kind of true, or why we can do that by using some prior knowledge. Clearly these two match at infinitely large data sets, right? Because then they wouldn't matter anymore. NH will be too large. They will just kind of disappear. What about priors other than uniform? So we saw now the effect of the uniform prior. For example, what if the beta distribution was used as the prior? Recall, what is a beta distribution? It's having 2 hyperparameters, alpha 0, alpha 1, and a normalizing constant gamma. So this is the notation, beta of alpha 1, alpha 0. The PDF will look like this. You see, it's very similar to the general form that we have for our likelihood in the coin toss problem. Theta to the power of alpha 1 minus 1, 1 minus theta to the power of alpha 0 minus 1. And these are a few examples of how the PDF will look like. The special case of beta 1, 1, this makes this equal to 1 and this whole thing equal to 1. So it's just a normalizing factor, and that will be 1. It's exactly the uniform distribution that we dealt with. Beta 2 and 2, you see these are the shapes, and we can have different distributions with by playing with the parameters. Okay. So what if I have used this one instead of the uniform distribution? It's not difficult to see then that then the posterior mean would look like this form, would be equal to this, alpha 1 appearing in the numerator and alpha 1 plus alpha 0 in the denominator. For example, if n of h was 6 and n of t was 4, then if I used beta 1, 1, this is what we use in the example, theta bar would be equal to this value. If I use beta 2 and 2, it will be 0.57. 10, 10, it would be 0.53. So it's decreasing here. And what was the MLE? Well, it was just 6 divided by 6 plus 4, which is 0.6. For large enough data instances, again, the posterior mean and the beta prior will be close to each other. It's like the posterior mean is with the beta prior approximates the MLE. So this is to show the effect of a different prior on the theta bar value. But what about categorical variables with more than 2 values, multinomial distributions? For that, we can use the Dirichlet distribution, which is a natural extension to the beta distribution. So if we have, instead of 2 variables that add up to 1 and are between 0 and 1, if we have k of them, say theta 1 to theta k, each taking a value between 0 and 1, and they all add up to 1, so they're basically representing a probability distribution, then we can use a Dirichlet distribution. The notation to say that the variables theta 1 to theta k, which are represented in a compact form as theta, following a Dirichlet distribution, is here, where alpha 1 to alpha k are the hyperparameters. The PDF will be simply the multiplication of theta k to the power of alpha k minus 1 over all values of k. This is the joint distribution of all of these variables. The expected value of the kth variable will be its hyperparameter divided by all of the summation of the hyperparameters, and the mode will be alpha k minus 1 divided by the summation minus k. Okay, and what can we say about prior posterior? Well, we have this very useful proposition. If I have a random variable that takes k possible values, so a categorical value variable, and moreover, the different probabilities for each of these values follows a Dirichlet distribution. So if I denote each probability for each of these values by theta k, by a parameter theta k, the prior distribution, I'm assuming, follows a Dirichlet distribution with parameters alpha 1 to alpha k. Now, imagine I have this initially, then suddenly I use a data set, I take some samples, and I want to update my distribution, so the posterior. How will the posterior look like? It will be a Dirichlet distribution again, and also the only thing I have to do is to just count how many times each of these cases will happen, n of x1, n of x2 to n of xk, and then just add them up to the corresponding hyperparameters. This means that if I have a Dirichlet distribution, the only thing I need to do after observing a data set and to get my posterior is to just count the number of different instances and update the hyperparameters. Okay. Now, just note that the posterior mean that we were calculating, this is the same as the posterior predictive distribution. What is a posterior predictive distribution? Recall, using the posterior, we can predict new instances. So consider a random variable x whose probability distribution is parameterized by theta. Given the observed data set x1 to xn, the posterior predictive distribution, or also known as Bayesian estimator, is the probability of the n plus 1 instance of x to take a particular value x condition on the observed data set. So we're calculating the probability distribution of my variable of interest x given that I already have observed n values. So it's basically to predict the next possible value. If I'm tossing a coin n times, what will be the n plus 1th toss given that I already made n observations? That's why it's a predictive distribution or an estimator. Now this equals to, when I put in theta in the probability and marginalize it using the integral, then this can be written using the conditional probability as condition on theta times p of theta condition on d. And then this term, I can take out d, because once I know the parameters theta, which determine the values of the probability of x taking a particular value, then I no longer need the observation or the data set. So I can just remove it here. Now, in the particular case of a multinomial distribution, if I want to calculate the particular value of x, say xi, then the posterior predictive distribution will equal, using this integral, will equal this term. So first of all, I don't need the whole theta anymore. I'm just focusing on xi. So I will have theta I here. This is the posterior. Secondly, this here, this is just by definition theta I. Okay. and the n plus 1 doesn't matter, it's just a new instance. So it will be equal to theta I, replacing it here. And now if you look at this term, this is just the expected value of theta I condition on the data. So it's the mean of the posterior, or the posterior mean. So I'm averaging theta I with not the distribution of P of theta I, but with the distribution of P of theta I condition on D. So at least in the multinomial distribution, interestingly, the posterior mean is the same as the posterior predictive distribution. Okay, so all those relationships between the MLE and the posterior mean, they also hold for posterior predictive distribution. It was like we were calculating the probability of a new instance using the data set. That was the same as the posterior mean. Now, here I have a useful result. Consider the multinomial variable x taking k values from x1 to xk, which is parameterized by theta, where the probability of the kth value given the parameters is simply theta k, and consider the data set D x1 to xn. If the prior distribution of x is a Dirichlet with hyperparameters alpha 1 to alpha k, then after observing this data set D, the posterior mean and the Bayesian estimator, they are equal to each other. Here's the notation for the posterior mean and the Bayesian estimator. They equal to this term, which is simply for the kth value, for this kth parameter, it will be the hyperparameter for k, alpha k, plus how many times we observed the kth value in this data set, n of xk. And of course, divided by the summation of the hyperparameters plus n, the size of the data set. That's simple. So updating my belief about x is as simple as counting how many times it appeared in the data set. And the posterior mode equals this term, which is the same as the previous one, with the difference that we have these additional minus 1s. They accumulate as minus k in the denominator. Now, if I use a uniform distribution where I put alpha i's equal to 1, we saw the case for the beta distribution, then this one, we see that it's the same as the MLE, with the difference that we have those additional imaginary 1s, plus 1s. But then in the posterior mode, I see that they cancel out, and then I will get exactly the MLE as before. Now, if we want to avoid those 0 cases that we discussed before, we can have the smoothing effect of adding a plus 1 here for a uniform distribution. We can use the posterior mean. In the next section, we will discuss the application of this framework to parameter learning in Bayesian networks. Thanks for your